Hi, let's continue with a few more problems from the harmonic oscillator section. Okay, as I said before, this is an important section with respect to the competitive exams. Okay. All right. So the first problem is this: a particle of mass m is placed in the ground state of a one-dimensional harmonic oscillator potential of the form v of x equal to half kx square. All right. You see that k is equal to m omega square. All right, where the stiffness constant k can be varied externally. That's the situation we have got. The ground state wave function has the form psi of x is proportional to e raised to, it's supposed to be an a here, e raised to minus ax square root of k. All right, they have given you the proportionality of the ground state wave function. So you don't have to remember anything for this particular problem. Everything is given here, where a is a constant. If suddenly the parameter k changed to 4k, the probability that the particle will remain in the ground state of the new potential. Okay, so we have got an old ground state. Okay, so we have got, what we have is an old ground state corresponding to let's say the value k. All right, and we have got a new ground state. We have got a new ground state for the second system where k has gone to 4k. These are the situations. All right. Now we are asked the question. It starts in the old ground state. The system is in the old ground state initially. It's in an eigen state of the energy. All right. Now we change this thing. Okay. Now if you make a measurement of the energy, you are trying to make a new measurement. You are making a measurement of the energy. And what's the probability that you will find the system in the new ground state? All right, that's the question. All right. So if it's in the old ground state and we are not doing anything, whenever you make a measurement, you will always find it in the old ground state. All right, that's the idea of being in an eigen state of some operator. Okay, but now something has changed, and now we have got some new ground states. What's the probability that the wave function will collapse in the language of Copenhagen interpretation? What's the probability that the wave function will collapse to the new ground state? That's the question. All right. So the basic idea is easy. We have done such a similar problem when we were doing infinite square wave potential. All right. We have done a similar problem there. So if phi is the new ground state and psi is the old ground state. All right, this is the old ground state and this is the new ground state. All right, so the probability for finding the particle in the new ground state after making a measurement of energy, for finding that, we had discussed this. In order to find that, what we do is that we project the given state, the initial state, to the final state. All right, we project it to the new ground state. All right, this will give you the expansion coefficients, and if you take the modulus square, this will give you the probability for finding the particle or finding the quantum mechanical system in the new ground state. All right, so we need to write down the old ground state, we need to write down the new ground state, and just do this thing. That will give you the answer. Okay, let's see how to do this. All right. So before going into this, when you work with harmonic oscillator problems using the wave function, right? Normally, most of the problems, the ground state wave function will be sufficient. You will be working with the ground state wave function of the harmonic oscillator potential. Okay, and over there are integrals which appear, which are called Gaussian integrals. All right, because the ground state wave function has a form, Gaussian form, e raised to minus ax square. Okay, that form is called the Gaussian form, and integrating such wave functions is for that you need some tricks to solve Gaussian integrals. All right, there are several ways to do that. One such way is to use the gamma function. All right, you might already be familiar with the gamma function. So gamma of z is integral 0 to infinity t raised to z minus 1 e raised to minus t dt. Okay, maybe it's a good thing to keep this in mind. Okay, you should be able to use it. Some of the previous net questions, they give you this relation. They give you the wave function and they give you this formula. All right, and you may be able to use it. Okay, so using this, let's find integral minus infinity to infinity e raised to minus x squared dx. Okay, this we can write as twice integral 0 to infinity e raised to minus x square dx. All right. Now we can bring it into the form of a Gaussian integral by making this substitution. We say that x square is equal to t. All right, x square is equal to t, or x equal to square root of t. All right. You make this substitution here. This means that dx is equal to 1 by 2 root t multiplied by dt. Okay, you make the substitution here, and then you see that it comes to the Gaussian integral form. all right, with this 2 and this 2 will get cancelled. It's e raised to minus t raised to minus half dt. Okay, so we have got t raised to z minus 1. Here we have got t raised to minus 1 by 2. So we compare, we say that z minus 1 is equal to minus 1 by 2. So z is equal to 1 by 2. Okay, the result for this is gamma of z. It is gamma of z. So it's gamma of 1 by 2, which is a known value square root of pi. Okay, that's how we do this thing. Alright. Now, we may need some practice with this if we are working with wave functions. Alright. So far, most of the problems that we did was using the creation and annihilation operators or the raising and lowering operators. But sometimes you may have to use the ground state wave function to do problem of this sort, for example. So you need to familiarize yourself with such integrations. Okay. So first, we have to normalize the wave function. Right, so we know that the wave function is proportional, the initial wave function is proportional to e raised to minus ax square square root of k. Alright, so it's a square integral minus infinity to infinity e raised to minus 2ax square root of k dx equal to 1. That's a normalization condition. Alright, so we are assuming that it's along minus infinity to infinity. So when you say that you have to normalize the wave function, what you mean is that it is somewhere along this line. It has to be somewhere along this line. Alright, so we say that minus infinity to infinity a square minus infinity to infinity psi star of x psi of x dx has to be equal to 1. You have to choose a in such a way that this condition is satisfied. Then we say that the wave function is normalized. That's exactly what we do here. Since it's a real wave function, the complex conjugate is the same, and when you multiply it with the complex conjugate, you get twice e raised to minus 2ax square root of k dx. Okay. Now this can be integrated. Right, this can be integrated. We'll try to bring it into the Gaussian form. Right, you can either bring it to the Gaussian form and repeat the steps that we did earlier. That's what we have done here. All right, or we could make this substitution we can make the substitution 2ax square root of k is equal to y square. All right, so this means that x is equal to y divided by 2a square root of k whole raised to 1 by 2. We are taking square root. Okay. So dx is equal to dy divided by 2a square root of k 1 by 2. So we make this substitution here. We make all the substitution here. So what we get is a square integral minus infinity to infinity. This simply becomes e raised to minus y square. Okay, and then you have got a dy divided by 2a square root of k whole raised to 1 by 2. Alright, because instead of dx we are substituting dy divided by 2 square root of k whole raised to 1 by 2. Okay, now we can pull this outside. We are demanding that this is equal to 1. Okay, this is the condition that we are demanding to find a. Alright, so this is a square divided by 2a square root of k whole raised to 1 by 2 is multiplied by, what's this integral? We have already done this integral using the Gaussian. Alright, we have already seen that this integral can be done using the gamma function. Alright, we already did it and we saw that the result is square root of pi. Okay, this is equal to 1. This means that a square is equal to 2a square root of k whole raised to 1 by 2. Okay, maybe we can put it all inside the root, square root divided by pi. Okay, so that's the answer. All right. So this means that a is the square root of this again. So it's 2a root k by pi whole raised to 1 by 4. Okay, so that's how we can do this. All right. So here we have used the gamma function again. All right, and we get a gamma of 1 by 2. So this is supposed to be a gamma, not a square root. Right, so we can try this. Okay, so you get some practice with such integrals. Now it's also a good thing to remember, at least. All right, sometimes it's sufficient to remember that this integral, all right, minus infinity to infinity, e raised to minus x squared dx is equal to square root of pi. Okay, this is considered as a standard integral, and if you remember this, some of the problems can be solved without going into the details of the calculation. All right, there are some integrals which we can bring it to this form directly, as we did here by making a substitution. All right, in that case the answer will be square root of pi multiplied by some constant, as in this way. All right, so this is supposed to be a gamma function here. Here in this step I have used the gamma function directly. Okay, it's not a square root, it's a gamma function. I'll correct it in your notes. Okay, here what I did here is I've used the result that we already got in the previous slide. Okay, that result is integral minus infinity to infinity e raised to minus x squared dx is equal to square root of pi. All right, so this is the normalization constant for the old ground state. All right, it's the normalization constant for the old ground state. Now we are supposed to find the normalization constant for the new ground state. All right, but that I think can be directly found from here, because the change between old and new potential is k going to 4k. So we just make a substitution here. Instead of k you put a 4k, and that 2 will come outside. So that answer is 4a square root of k divided by pi whole raised to 1 by 4. All right, that's a normalization constant for the new ground state. All right, so we are here. I have given the calculation so that you can check. Just try to calculate this once more. All right, we are taking the new ground state as psi of x is equal to b e raised to minus ax square to root k. All right, to root k, because instead of k we are substituting 4k. Right, so that square root of 4k, that 2 we have pulled out here. All right, so you can try the integration can be done in exactly the same way using the gamma function or the result that we got before. All right, finally you are supposed to get this thing. All right, so try this. Okay, so in an examination, if such a problem is asked, this is the easiest way to do. All right, you can directly substitute k going to 4k in this thing, and we get the same result. Okay, b is equal to 4a root k by pi whole raised to 1 by 4. All right, so these are just some things that you have to get some practice with. All right, so that you can solve problems in examinations. Okay, all right. So we have got two wave functions now, the initial wave function and the final wave function. All right, we have got these two wave functions. Now what did I say? The probability. So initial, this is the initial wave function. The probability that if you make a measurement of energy, the probability that you will find it in this state is simply psi f psi in, okay, modulus square. All right, so here that's exactly what we do in the position space. This bra psi f is psi f star. This is psi in dx. Okay, so this constants all can be pulled out and we get a rather simple integral here. It's minus infinity to infinity e raised to minus 3ax square square root of k dx. Okay, all right. This is the this is the expansion coefficient, and then we have to do the modulus square of it. Okay, all right. So I think we have pulled this 2 out here, so the limit of the integration can be written as 0 to infinity. If I am not mistaken, its psi in is yes. Okay, yeah, that's correct. All right, so this 2 is pulled out, so the integral becomes 0 to infinity. Right, so we'll correct that. And then again you can write it in the form of a Gaussian thing that we are familiar with. All right, you can write the result, this integral, as root pi multiplied by some factor. How do you do that? You just make the substitution. You put 3a x square square root of k is equal to y square. Okay, so this means that what do you say, x multiplied by 3a square root of k whole raised to 1 by 2 is equal to y. Right, so when you find dx, that's dy divided by 3a root k whole raised to 1 by 2. Okay, so then you can use the Gaussian function, or you can use the result for or you can use the result for what do you say, either we can use the Gaussian integral, or we can already use this result e raised to minus x square dx. This has to be equal to square root of pi. All right, so whichever way you do it, you go through these steps. It's not very difficult. Please go through these steps, and finally you make sure that this is the answer. All right, so this is the answer that I get here. You please check this. So this is only the expansion coefficient. All right, this is only the probability amplitude. So in order to get the probability, you just square this. Just square this thing. Okay, and it's 2.828 divided by 3, which is 0.94. right? So there's a 94% probability that if you make a measurement, you will find the system in the new ground state, right? There's a huge probability that after making the measurement of energy, the system will be found in the new ground state, all right? So you can go through the details of these calculations, check if these calculations are correct here, okay, and then we'll see. All right, so such problems can be asked. Okay, now here is another question. This has been asked for one of the previous NET JRF exams. All right, let 0 and 1 denote the normalized eigenstates corresponding to ground and first excited states of a one-dimensional harmonic oscillator. The uncertainty delta p in the state 1 by root 2 0 plus 1. All right, so our wave function is given like this. Our wave function is given like this. Psi is equal to 1 by root 2 0 plus 1. Okay, so we are supposed to find delta p. How do we find delta p? The relation for delta p was this. It's square root of expectation value of p square minus expectation value of p square. Okay, this is expectation value of the square minus square of the expectation value. Okay, this is delta p. All right, now what do you mean by this expectation value of p? This means in the state psi, this is psi p psi. So instead of psi here, now we have to use this state. All right, that's all. So let's do it. It's not very difficult. First, we need expectation value of p. All right, what we do is we write p in terms of a dagger and a. We know that p, you might already remember that p can be written as I square root of h cross m omega divided by 2 a dagger minus a, right? And this is the wave function. So expectation value of p is psi p psi, right? So we just plug in the wave functions here. It's 1 by 2 because there is a 1 by root 2 from both parts. We put it together here as 1 by 2, and then this is bra 0 plus bra 1 and a dagger minus a, and then ket 0 plus ket 1, and then there is this constant factor I square root of h cross m omega by 2 outside. All right, now you don't have to go into all these terms. We can take only the non-zero terms. Okay, we need to take only the non-zero terms. Okay, for example, if we check this combination 0 a 0, we know that it will go to 0 because 0 a dagger 0, a dagger acting on 0 will give you 1. Okay, a dagger acting on 0 will give you the state 1, and then 0 with 1 is equal to 0 by orthonormality. All right, so similarly 1 a dagger 0, that's non-zero because a dagger acting on 0 will take it to 1, and then that's non-zero. All right, but 1 a 0, that is 0. Similarly 1 a 1, that's also 0. There is one more possibility. There is 0 a 1, that is non-zero. Okay, so we need to take only those terms which are non-zero. So here we see that the non-zero terms are just this 0 a dagger. No, there is no combination. So it's 1 a dagger 0 because this a dagger will take 0 to 1. That's one combination. And then there's another combination. There is 0 a 1 because this a will take this 1 into 0. Right? You will see that these are the only non-zero terms. So we don't have to write down all the terms here. You can try writing down all the terms and you will see that it's 0. Right? So we write only the non-zero terms here. It's 1 a dagger 0 minus 0 a 1. Right? What happens when a dagger acts on 0? You get 1. So it's 1 1 minus 0 0. And what's this? This is 1 minus 1. So that's equal to 0. So the expectation value of p in the given state, all right, the expectation value of p in the given state is 0. Now we need to find the expectation value for p square. That's what we do next. P square is minus h cross m omega because I square gives you minus 1. Minus h cross m omega by 2 a dagger minus a whole square. Okay, a dagger minus a whole square. So it's h cross m omega by 2. Now we square it. Okay, it's a dagger square plus a square minus a dagger a minus a dagger. Okay, that's p square. Alright, I think I missed a minus sign here. There was a minus sign, so that minus sign will get here. So now what we do is that we find psi p square psi. So we sandwich this operator between the states psi. That's what we do here. We'll first pull out all the constants out. Okay, it's minus h cross m omega by 2, 1 by 2. Okay, and then we have got here 0, 1, bra 0 plus bra 1, and here ket 0 plus ket 1, and in between we have the operator part. Okay, this is part of p cap. Right? The rest of them have been taken outside. Right? Again, you need to take only the non-zero parts here. Right? You need to take only the non-zero terms. Okay, that makes things rather easy. Without writing down all the terms, by inspection you can find the non-zero terms. How do we pick out the non-zero terms? Okay, so how do we pick out the non-zero? So you see that here there is a dagger and a dagger square and a square. Right? So which means that a dagger square on acting 0 and 1. Okay, a dagger square will take it to a state 2 and it will take this to a state 3. Am I right? Because a dagger acting twice, acting once will make it to 1, ket 1, acting once more will take it to ket 2. Right? Similarly, a dagger acting on this twice, acting once it will take to 2, acting twice it will take it to 3. Alright, so let's not worry about the normalization part here, but you see that this becomes 2 and 3 when a dagger acts, a dagger square acts. Am I right? And there is nothing to combine, it will give 0. 0 with 2 is 0, 1 with 2 is 0, similarly 0 with 3 is 0, and 1 with 3 is 0. That's orthonormality. Alright, so you see that the terms on which a dagger square acts will vanish in the end, so you don't have to write down. In the same way, a square acting on 0 is 0, so that's 0. A square acting on 1, that's also 0, so there is no contribution from that. Okay, so the only terms that we have is a dagger a minus a dagger. Right, a dagger a minus a dagger. We pull this minus outside and it's plus h cross m omega. We have got a dagger a plus a dagger. Right, we pull this minus outside. Okay, now we have to be a little bit, now we can again see that you don't have to write down all the terms. All right, so since we have a dagger and a on both terms, we have got a dagger a plus a dagger. Right, since we have this, we know that the only terms, okay, the only non-zero terms will appear when exactly the same state appears on both sides. Okay, so when this comes in a balanced way, a dagger and a, all right, the only non-zero terms correspond to happen when both the states here are the same. So we don't have to take the combination 0 a dagger a plus a dagger 1. This combination is 0 clearly. All right, you can check that. Okay, so we take only the non-zero term. Since a dagger a minus a dagger, so minus a dagger a minus a dagger is the only term, that's why we write it here. Right, and then we see that the non-zero term corresponds to only when both these terms are the same, both these states are the same. All right, the other combinations we can get rid of now itself. All right, now if you are not convinced about this, you can just try it. All right, try all the terms just for the practice. All right, and you will see that, okay, I want you to try this as an exercise. All right, you will see that when terms like this appear, a dagger a or a dagger, okay, if it appears, then the non-zero terms appear only when the states here are exactly the same. Right, if the states here are exactly the same. Okay, otherwise the answer is 0. That's not very difficult to see, because for example you have got a dagger a acting on n. Okay, this is the operator n cap. This is eigenvalue n multiplied by the ket n. This is the eigenvalue equation. So the only non-zero term comes for only if n is, you have got exactly the same n here. Right? Otherwise, by orthonormality, that term will vanish. So just remember this. If a and a dagger appear equal number of times, then the non-zero terms correspond to those terms where these two states are the same. Okay, so we take only those terms with the same state on both ends and neglect the other terms, or get rid of the other terms because these are 0, and then we write it like this. Right, and here it's a dagger plus a dagger a 0. Okay, a dagger plus a dagger a acting on 0. What happens when a dagger a acts on 0? You get 0. Right, what happens when a dagger acts on 0? Because a acting on 0 is 0. Okay, a acting on ket 0 is 0 by definition. This is 0. All right, so let's not worry about this term. A dagger acting on 0. What happens to that? A dagger acting on 0. A dagger acting on 0 just gives you, or we have already seen that A dagger acting on n is equal to n plus 1 multiplied by n. Okay, if you remember from our previous class. Okay, because A dagger acting on this takes it to state 1. Okay, and A acting on it again takes it back to the state 0. So what we have is actually bracket of 0 with 0. Okay, bra 0, ket 0, and that combination is 1. That's why we have got a 1 here, right? And what about the other term here? We have got A dagger plus A dagger A acting on 1. Okay, A dagger A acting on 1 gives you 1, the eigenvalue 1. Okay, and this A dagger gives you n plus 1. Okay, that's 1 plus 1, that's 2. So 2 plus 1 is 3. So it's h cos m omega divided by 4 multiplied by 1 from here and 1 from here and 3 from here. Okay, 1 from here and 3 from there. Okay. Alright, so that's simply h cos m omega. What's this? This is expectation value of p square. Right, now delta p is square root of expectation value of p square minus square of expectation value of p. Okay, so it's just the square root. This term is 0, we have already seen. So it's simply square root of h cross m omega. Okay, so the answer is square root of h cross m omega. So if you, this is a question that was asked for one of the previous examinations. You see that that answer is somewhere here. It's option C. Yeah, it's square root of h cross m omega. Right. Now, I want you to get some practice with this, all right? It may look rather trivial when you look at it in this way, but you try it yourself. You try it yourself and convince yourself about which terms will go to 0 and which will remain, etc. So, please try this, get some practice with such problems. You should be able to solve a few problems. You should be able to solve such problems if they appear in examinations, all right? So, try, work it out. Work it out yourself. Alright, so the only way to do these things fast is by getting practice and convincing yourself that certain terms, those that I mentioned, will be 0 always, and you don't have to write them all down immediately. Alright, and by inspection you can find the non-zero terms and write down only the non-zero terms. That will save you a lot of time and space. Okay, alright. Let's go to the next one. Consider the normalized state psi of a particle in a one-dimensional harmonic oscillator. This is the state, all right? It's the same kind of state that we saw just before some time, where 0 and 1 denote the ground state, ground and first excited state respectively. This was also a previous net question, okay? This was also a previous question. And B1 and B2 are real constants. The expectation value of the displacement x in the state psi will be minimum. All right, what's the condition for the expectation value in this state for x? All right, expectation value of x in this state is minimum. Okay, so what we do is we start by finding the expectation value of x in this state. All right, we start by finding psi x psi, and we know how to do this. We have already done these things. We substitute for x in terms of a and a dagger. Right, it's square root of h cross by 2 m omega a dagger a. This is simply your x, and we just put the states here. It's b1 0 plus b2 1. This is psi, bra. This is ket psi, and this is bra psi. Okay, all right. Now we can look for the non-zero. We pull these constants outside. It's square root of h cross by 2 m omega. Okay, we see that. Now we can look for the non-zero terms, all right? So you see that this 0, when coming here, there's no term that it can combine with, okay, if it's a dagger, because a dagger acting on 0 will give you 1, a dagger acting on 1 will give you 2. Okay, I'm talking about ket 1 and ket 2, of course, all right? So you cannot combine it with this 0, okay? Now, what about this? If it comes a here, a acting on 0 is 0, so that term you need not take, but a acting on 1 gives you 0. So that's one non-zero term, all right? That's one non-zero term, all right? So the only non-zero contribution from this, when you combine, it comes when you combine it with a. Okay, that's why I've written here. It's b1, b2, b1, b2. It's all right. The first I've written it here. It's b1, b2, 0, 0, a, 1. Okay, that's one term. What about this term? 1, b2. When a dagger acts, right? When a dagger acts on 0, it will give you 1. So that will be a non-zero term because this is 1. Okay, that's non-zero term. All right. But a dagger, okay, let's look at this term 1a. Alright, there is no combination because 1A0 is 0, 1A1 is also 0 because A acting on 1 will take it to 0 and by orthonormality it will be 0. So, there are only two non-zero terms here. One is 1 A dagger 0 and 0 A1. I think it's rather obvious. We can just try it. Okay, if you don't believe this thing, just try by taking all the possible combinations. Alright, take all terms and try. Okay, so you see that by orthonormality these are the only non-zero terms. 1 A dagger 0 because A dagger acting on 0 will take it to 1. Similarly, A acting on 1 will take it to 0 at the state 0. Right? And the corresponding coefficients are B1, B2, B1, B2. Now, what's 1 A dagger 0? A dagger acting on 0 is simply the state 1. The normalization constant is 1. So, this is simply B1, B2. What about this? A acting on 1 is square root of 1 multiplied by the state 0 and that's simply the state 0, right, or the ground state. But this thing 0 with 0 is equal to 1. That's orthonormality. Okay. So, what you have here from is square root of h cross by 2 m omega 2 B1, B2. Alright. Now, let us take a step back and look at this. Alright, this is what we have. Right, we have got two things here, B1 and B2. Okay, but we see that this B1 and B2 are not independent. Why are they not independent? Because it's given that it's a normalized state. It's a normalized state, which means that there's a relation between B1 and B2. B1 square plus B2 square is equal to 1, or B1 is equal to or B2. You could do it either way. B2 is equal to square root of 1 minus B1 square. So, we can write this in this term 2 square root of h cross by 2 m omega B1 square root of 1 minus B1 square. That is the expectation value of x. Right. Now, what's the value for B1 for which this is a minimum? What's the value for B1 for which this expectation value of x is a minimum? Right. This is a usual, this is a typical problem of finding the minima of a function. Right. So, here you can vary this function, you can vary this expectation value with respect to B1, demand that this is equal to 0. Right. This is a problem for minima, for finding the minimum. Find the minimum. So, generally if you have a function f of x, how do you find the minimum of it? You say df by dx equal to 0. You solve this, you solve this for x and you will see the minimum point. Okay. In the same way, what's the value for b1 that gives the minimum value for this combination? Alright. So, you take the derivative with respect to b1 and demand that this is equal to 0. That's what we do next here. Right. Since we are demanding it to 0, these terms will immediately disappear and we can write, you just take the derivative, it's a product rule, it's b1. Okay, keep this thing constant and then take the derivative of this. All right, it's b1 1 by 2 square root of 1 minus b1 square multiplied by minus 2 b1. Okay, taking the derivative. Okay, taking the derivative. The derivative is this. Okay. All right. Now you keep this a constant and then take the derivative of b1 with respect to b1 and you get square root of 1 minus b1 square is equal to 0. Okay. Now you just solve this equation for b1. You see that 1 minus 2 b1 square is equal to 0 or b1 is equal to square root of 1 by 2. Okay. Once you find b1, b2 is equal to square root of 1 minus b1 square. Okay. That's also square root of 1 by 2. So, the expectation value of x has to be a minimum for b1 equal to b2 equal to square root of 1 by 2. Okay. So, that's the answer. The expectation value of x is a minimum for b1 is equal to b2. Alright, you will see that such an option is there. Even though they haven't given the value for b1 and b2, they have given b1 has to be equal to b2. So, the best option here is option D. Okay. Alright. So, if b1 is b2, it's clear that it has to be 1 by square root of 2 because it's a normalized state. Okay. So, I hope that's clear. Just do this again and see if you are sure about this or if you are sure about the fact that these are the only non-zero terms. Okay. All right. Here is one more problem. This also was asked for a previous net examination, net JRF examination. Okay. A particle of mass m in the potential v of x comma y is equal to half m omega square for x square plus y square is in an eigenstate of energy E is equal to 5 by 2 h cross omega. Alright, the energy eigenvalue is given. The corresponding unnormalized eigenfunction. Okay, you don't have to worry about the normalization factor. You want to find the unnormalized wave function. How do you do this? Okay, so the energy is given. So what we do is that we'll do the usual trick. We'll write this V as half m omega square for x square, okay, plus half m omega square y square. Right, now this you can write as half m 2 omega square x square plus half m omega square y square. Alright, so you can consider this as an oscillator with frequency 2 omega and this as a oscillator with frequency omega. Alright, that's exactly what we'll do. Okay, it's this. Alright, so v of x comma y is written as half m 2 omega square x square plus half m omega square y square. Alright, now if this is the potential, we know how to find the eigenvalues. Alright, if the potential is half m omega square x square, we know that the eigenvalues we can write as n plus half h cross omega. In this case, we'll write as nx. Okay, because there are two dimensions. H cross omega in term h cross omega x. Alright, corresponding to this thing. Alright, and this is ny plus half, the corresponding energy eigenvalues ny plus half h cross omega. Okay, now this omega x is 2 omega and omega y is omega. So we can write it as nx plus half h cross omega x plus ny plus half h cross omega y. Right, now omega x is 2 omega, omega x is 2 omega and omega y is simply omega. Right, so we can write it in this form. Now you add them up, just multiply it inside and add them up. You see that the expression for energy eigenvalue is 2nx plus ny plus 3 by 2 h cross omega. Okay, I think we have already done a problem where part of it was similar. All right, so now we know that this has to be equal to, because it's given that this value is 5 by 2 h cross omega. Okay, this value is 5 by 2 h cross omega. This is given in the question. So what's nx and ny corresponding to this? You see that you will get this will be equal to 5 by 2 h cross omega only if you put nx equal to 0 and ny equal to 1. Alright. So now we know the values nx equal to 0 and ny equal to 1. Okay. So what you need to do now is that you write down the wave function for nx equal to 0 in the x direction, write down the wave function for ny equal to 1 in the y direction, and the product of that would be your required answer. Okay. So let's look into that. Alright. So here what we have is the wave function is given. We have seen the energy eigenfunction for harmonic oscillator in one dimension is given in terms of the Hermite polynomials, and there's this part here. We have seen this is the normalization constant, but we are not worried about the normalization constant now. Alright, and we also have h. So this is for one dimension. Right, so we also have these results. h0 of y is equal to 1 and h1 of y is equal to 2y. Right, h0 of y is equal to 1 and h1 of y is equal to 2y. All right. So now you construct this wave function. You will take only this part. Okay, we'll take only this part. All right. So we have got one part of the wave function will be e raised to minus x square divided by 2x square. And what's 2x square? Let's because x0 square e raised to minus x square, okay, divided by 2x0 square, okay, 2x0 is square root of h cross by m omega, so x0 square is h cross by m omega, okay, and in the x direction we said nx equal to 0 and it's h0 of x by x0, but h0 is anything is 1, so you've got a 1 here. Okay, so we'll write it as m omega x. All right, so that's one part of the wave function. We have got minus x square, and this you can simply write it as m omega x divided by 2h cross. All right, that's what we have here. Right, minus x square m omega x divided by 2h cross. Right, similarly, what's in the y direction? We know that in the y direction ny is equal to 1. So that correspondingly we will have e raised to minus y square divided by 2 m omega by 2 h cross by m omega. Right, so that's let's write it like this. In the y direction it's e raised to minus y square divided by twice h cross by m omega, right? And then what you have here is h, let's write as m omega y to be sure, all right? And then we have got h1 of whatever, right? h1 of let's say y by this y0, y by y0, right? But h1 of y is 2y, h1 of y is 2y. Okay, you can maybe write y in terms of something else to make it so, all right. So this h1 of something is twice that thing, okay, and the other thing is a constant, so we are not worried about that because we need to find only the unnormalized wave function or non-normalized wave function, all right. It's 2y in this here. So what we do is that there is a constant also here, all right. So this is the wave function corresponding to the x part, and this is the wave function corresponding to the y part, all right. Then there is also of course a constant here, so let's not worry about that because we are leaving out the constants, okay. All right, so in the same way we can also leave this 2 out, okay. It actually has to be y by y0 here, but we are leaving out that part, okay. Now what appears here, we can now make the substitution omega x equal to 2 omega and omega y is equal to omega, okay. So then that becomes, we can pull this omega by 2 h cross outside and you will have a 2x square plus y square, all right. So this is the answer, you can check. So once you substitute omega x equal to 2 omega and omega y is equal to omega, you will see that the final answer reduces to this, okay. So you can check this and that's the answer, okay. And this option, this is the answer given in option A, all right. Of course there is this constant which I left out because we are not worried about constant factors, we are worried about the unnormalized wave function, okay. All right, so this is yeah, we can call this a psi nx of x and this is psi ny of y, right. We just multiply the corresponding wave function to get the two-dimensional energy eigenfunction, okay. Now you see here that in order to do this problem, right, I have taken this question directly out of a previous question paper. In order to do this thing, you had to remember h1 of y is 2y, all right. You had to remember this fact. So remembering this wave function has helped, okay. Remembering this wave function has helped, all right. So I suggest that you memorize this wave function, all right. If you cannot remember the normalization part, okay, if you can remember the whole wave function, it's better, and at least for a few values of hn, all right. So this h0 of y, we know it's 1, but h1 of y is equal to 2y. This also you had to remember, and those who remembered this particular answer, this particular result, h1 of y is equal to y, could have answered this question, all right. We have to be a bit careful here because you write omega x here and omega y here. You have to remember that omega x is equal to 2 omega and omega y is equal to omega, all right. And then you will get this final answer, all right, because omega x is 2 omega, that's why we have got a 2x square and a y square there, all right. So that's also not a very difficult problem. Only thing is that in order to do this, you have to remember a few things. All right. So please go through these things. Now, what do we have here? The motion of a particle of mass m in one dimension is described by Hamiltonian h is equal to p square by 2m harmonic oscillator potential plus lambda x. Okay. Again, this is a previous question. All right. Here they have asked, what's the difference between the energies of the first two levels, right? Now we know that we have done this problem. We know that we can complete this square and write it as the energy eigenvalue plus a constant, all right. You will see that the energy eigenvalue will go like this. That's the usual harmonic oscillator plus or minus a constant. Okay, if you remember from our previous class, we have done such a problem where we can complete the square and we see that this Hamiltonian can be written as the usual harmonic oscillator Hamiltonian plus a constant. Okay. Now since this is a constant, when you take the difference of energies in the first two levels, this constant will simply disappear. All right. So what you need to do is you simply have to find En plus 1 for the harmonic oscillator minus En. So this is n plus 1. This is n plus 1 plus half h cross omega minus n plus half h cross omega. So they have asked for the first two levels, so we can put n equal to 1 and n equal to 0 here. So this is actually 2 plus half h cos omega minus this is half h cos omega. All right. So the answer happens to be, is that correct? Yes. What's the answer? The answer happens to be, did we make a mistake? Okay, sorry. So for n equal to, okay, I think I made a mistake. All right, so I'm sorry. What we had to do is we have asked for the first two levels. All right, so since they both differ only by this constant, we can write, we can write E1 is equal to 1 plus half h cos omega, and E0 is equal to 0 plus half h cos omega. All right, because n equal to 0 value is possible. So this is 3 by 2 h cos omega minus 1 by 2 h cos omega. Okay, and that's simply h cos omega. All right, option D, that's the answer. Now I've given the detailed calculation here. You can go through that and convince yourself that this is actually true, this is actually correct. Okay, all right. Now I've added a few exercises. We already found the uncertainty in delta p. Okay, for this state psi, we already found this. I want you to find for delta x. Okay, correct this question as delta x. Delta p already we found. I want you to find the uncertainty in delta x. Okay, in this particular state. The answer is square root of h cross by 2m omega. So please do this. We can look at the steps that we did for finding delta p and see if you can get to this answer. Okay, the next exercise, the energy eigenvalues of a particle in a potential half m omega square x square minus x. This also was a previous question. Again, you see that you can write it, you can complete the square and write it as a harmonic oscillator potential minus a constant term, and then the energy eigenvalues will differ accordingly. All right, you can check that and do it. Okay. All right. So with that, we'll complete today's session. Thank you.